Let's consider problem 8.24 of Sonntag, in which we have been given a heat engine which receives 6 kilowatt from a source of 250 degrees Celsius and it rejects heat at 30 degrees Celsius. So schematically we have 250 degrees Celsius over here and sink of 30 degrees Celsius. So the heat engine is receiving 6 kilowatt. It is rejecting heat like this. There is some work output. So we must see which one respects the inequality of Clausius. So the inequality of Clausius is integral del q by t is less than equal to 0. The equality holds true for a reversible process. So A W dot is equal to 6 kilowatt. So if W dot is equal to 6 kilowatt, then all of the heat input is as good as converted into work. So QL, which is equal to QH minus W, will be 0. So this is not possible. As per the second law, this is not possible, but we have been asked to investigate the three cases with respect to the Clausius inequality. So integral del q by t, close to integral del q by t, in this case, because QL is 0, it will be only be QH by TH, and so the QH is equal to 6 kilowatt. TH is equal to 250 degrees Celsius, which is 253 plus 273.16. So clearly QH by TH is greater than 0, which is not possible. So this particular case, it violates Clausius inequality. The other case, so not only does it violate the Clausius inequality, it also violates the Kelvin statement of the second law, that there can be this, if W dot is equal to 6, then there is a complete conversion of whatever heat is absorbed into work. That is not possible. Second case is when W dot is equal to 0. So when W dot is equal to 0, QH equal to QL, and closed integral del Q by T is equal to QH by TH minus QL by TL. Here QH is given as, how much is it? 6 kilowatt. QL is also equal to 6 kilowatts. So closed integral del Q by T is equal to 6 by 250 degrees Celsius. And the amount of heat lost is also equal to 6 kilowatt. Okay, so the value of this is equal to to 6 by 250 plus 273.16 minus 6 by 273.16 plus 30. So the circular end is less than 0, which means that this process satisfies Clausius inequality. Satisfies Clausius inequality. The last case, we have to examine the case when it is a Carnot cycle. I guess that's the easiest one. So QH by QL, so QH by W is equal to TH by TH minus TL, 273.16 plus 250 divided by 250 minus 30. Doesn't matter if you take this in Kelvin or degree Celsius, because all we bother about is the difference. So this is equal to 523.16 divided by 220, and so QH was given to be 6 kilowatt. And so the W dot is equal to 6 into 220 divided by 523.16. So the W dot is equal to 2.523 kilowatt. So for the Carnot cycle, this is equal to 2.543 kilowatt, and 6 minus 2.543, which is approximately equal to 3.5 kilowatt, is rejected to the ambient. So in this question, the important concept is that if the cycle is working in a, so if the system is working in a cycle, so if you are working in a cycle, the integral of del Q by T must always be less than equal to 0. Equal to 0 hold true for reversible process, but in general it is less than 0. Because it is less than 0, we are always losing some amount of work in every cycle. If it's an ideal cycle, if it's a Carnot cycle, we are optimally converting whatever we could into work. It is not the case for an irreversible cycle.